This is another practice exam problem we're going to be looking at. We have this RL circuit, and first we're going to look at part F, where it's asking us to identify the filter type of the circuit. We're going to use the node voltage method to write the transfer function of this in a second, but we'll come back to that after we know the filter type. So if we look at the notes linked below the like button, we are going to see high pass filters, and they look something like this. Now, there are different ways they can look with RL or RC or CR, however you're memorizing it. They're very similar to previous low pass, but these are high pass. The high pass allows the higher frequencies to go in, and we also have examples of this where we actually have a load resistor in parallel with our inductor, or if we had a capacitor, we would have a load resistor in parallel with the capacitor. So it depends on how it's written, but this is kind of the base form of it. So if it looks something like this, that means it's a high pass filter. So the last part in part F is a high pass. Now we can work on solving this. And for the node voltage method, we know that we are going to have our V output be equal to our V input, and this is being multiplied by the impedance over our V out. We know this to be Z to the L, which is S times L in the S domain. So we're going to have S times L plus our last impedance, which is R right here. So this is what we're going to have. Now, we want to get S by itself. So what we can do is multiply both sides by 1 over our V input, and that's going to become H of S, right? Because we have H of S and this is equal to V out over V in. We're going to divide both sides by L now because we want S by itself. So we are going to get S over S plus R over L. And now we can plug in our values. So we're going to have 3.5 times 10 to the cubed divided by our 570 divided by 10 to the negative 3. And this is going to give us approximately, for our R of L, or our R over L, 6140. So the answer right here is going to be 6140. Now we need to find our omega C, which is the cutoff frequency. Previously, we used like H max to find it, where we had H of our omega C be equal to the H max over the square root of 2. That should look familiar from the low pass, but we're not going to do that with the high pass, because if we look up top right here, we plug in an S right here, that means our H max is going to be 0, and we're just going to have 0 over 2, and our H max is, our H omega C is not going to be 0. So that's not going to help us find it. So for high pass, we're just going to take what we have here and plug it into our omega C. So our omega C is just going to be equal to our R over our L. And we have kind of an example in the notes linked below the like button, where it looks like this. We have the omega C equal to 1 over RC. That's for capacitance. It's because it's written a little bit differently here. And we can see that right there. So we already found our R over L. This is 6140. And so that means our omega C is 6140 rads per second. Now for frequency, we're just going to use the formula. Omega C is equal to 2 pi times F of C. And so our F of C is going to be 2 pi over our omega C, which is 6140. And so our F of C is going to be equal to our omega C divided by 2 pi. And this is going to give us approximately 977. So our frequency is 977 hertz. Now we need to find the pass band, we need to find the phase angle at the corner frequency, and we need to find the stop band. So looking at the notes, we're actually going to use this equation right here for the phase response. Now I'm just going to copy it and paste it right here. We know we take the denominator angle and subtract it from the numerator angle, and we know that our omega is going to be 6140. And so when we plug this in for the first part, we need our omega to be much greater than our omega C. Well, if we were to plug something much greater in, let's just plug basically infinity in. So we have infinity over 0, not 0, but something very close to 0. So this would yield us basically, for the first one, C, tangent -1 of infinity. And tangent -1 of infinity is going to be about 90 degrees. Now we need to subtract the denominator angle from this, and we're going to basically have another tangent -1 of infinity because we're plugging in our omega here. So this minus this is going to give us 0 degrees. So for the first part, we're going to have 0 degrees here. Now we're going to look at D, where the phase angle of the output at the corner frequency, omega is equal to omega c. That's when they're the same thing. So when it's the same thing, we're going to still have some large number over 0 for the first part. So for the first one, we're going to have tangent -1, some large number, so we'll just say infinity, over a small number. And even if you plug in tangent -1 of 6/140, because remember they're equal here, we should have omega is equal to omega c. It's going to give us 90 degrees. So we'll have 90 degrees here, minus, this next part's going to be a little tricky. So we have our omega over r over L, and we can't just plug in an omega here, right? Let's actually, for clarity's sake, because they are equal, we're going to replace this with 6/140. And then here we're going to have tangent -1, 6/140 over 6/140, because RL we found up here. And so this is going to be tangent -1 of 1. And tangent -1 of 1 is going to be 45 degrees. So we have 90 degrees minus 45 degrees. This is going to give us 45 degrees. So our answer here is 45 degrees. Now for part E, it's going to be a little bit different. We can see that we have our omega much less than our omega c. And so that means our omega is going to be some really small value. We can say 0. And when we have tangent -1 of something over something, which in this case we would have tangent -1 about 0 over 0, this is going to be 1, so we're going to have tangent -1 of 1, which is going to give us 90 degrees. We're going to subtract this by the denominator angle. The denominator angle, we're going to have tangent -1, some really small value, which is like 0 degrees. And this is going to be over our 6/140. And then this is going to give us 0, because tangent -1 of 0 is 0, so minus 0. So the answer to this last part, part E, is going to be 90 degrees. And if we actually look at the notes linked below the like button, we scroll through it a little bit, we go through this example, we can see the frequency response plot is this. This is very similar to the example that we've done here. So this is what it would look like if we were to do a Bode diagram of it. We can see just by looking at it, our omega is much greater than our omega c at 0 degrees. And if we look at our example, very close, basically the same thing. We have the omega much greater than omega c at 0 degrees. Again, same thing we have here. At omega c, it's 45 degrees, which is what we have here. And then at the 90 degrees, or at 0, some very small value, smallest value it can be, it's going to be at 90 degrees, stop band. So that's how you'd look at this problem, and that is the theory behind it.